Hello, today's topic is Prim's algorithm. Before we begin with Prim's algorithm, it's very important to know what is a graph and what is a spanning graph or a tree. So, what is a graph? Graph is a set of vertices and edges which connect those vertices. So, what is a spanning graph or a spanning tree? I'll tell you the spanning graph and then I'll tell you why it is called as a tree. A spanning graph is a subgraph of a normal graph which includes all the vertices of the graph and only few edges of a graph. That is, it will have all the vertices that we have in a main graph. It is a subgraph of a main graph tree. But it is not necessary that we include all the edges. And it is also very important that the spanning graph doesn't have any cycles. So a spanning graph is a subgraph of a graph which does not have any cycles and which includes all the vertices of a main graph and few edges of the main graph. And the edges may not have the weight or may be assigned to them or may not be assigned to them. And the total number of the next question is how many spanning graphs are drawn using a single graph. So the total number of spanning graph with n number of vertices in a main graph will be creating around a graph with n number of vertices will create n into n minus 2 number of subgraphs, that is spanning graphs. So let us take an example. So this is a graph that we have with four vertices A, B, C, D with weights over that. So we can call this graph as a connected, weighted, undirected graph. It is connected because all the vertices are connected to one another, and it is weighted because we have weights over the edges, and it is undirected because there are no directions over the edges. So this is a graph that is undirected, weighted, connected graph. So let us see all the possible subgraphs of this one. So possible subgraph, as I said, subgraph are the subset that contains the subset of the vertices and the edges. And here we are concentrating on the spanning graph or a spanning tree. So spanning graph, so it has all the vertices of the graph but only few edges of the graph, so that it doesn't make or doesn't have any cycles. So these are few examples of spanning subgraph that are induced from a graph that we have with four vertices A, B, C, D which are connected to each other. So the leftmost first subgraph where A is connected to B, A is connected to D and D is connected to C, but there is no edge between B and C. This is the first subgraph or a spanning subgraph that is induced from the graph. So here the spanning subgraph have all the four vertices of your graph A, B, C, D. Yes, but it doesn't include one edge, that is B to C, which was weighing 1. If I had used this edge, it would have created a cycle. So since a spanning subgraph shouldn't have or doesn't contain a cycle, so we have deducted this edge B to C. Similarly, the second subgraph, spanning subgraph, A to D, D to C, C to B. There again, there is no edge between A to B because it will form a cycle. So in such a way, we will be coming across many subgraphs. So how many subgraphs? We'll find out that. Since our graph has four vertices, so 4 raised to or 4 to the power of n minus 2. N to the power of n minus 2. So 4 to the power of 4 minus 2. That is 4 to the power of 2. 4 to the power of 2 is equal to 16. So with this graph with 4 vertices and 4 edges, it will be inducing 16 spanning subgraphs. So this is about spanning subgraph. So the question was, why do we call it as a tree? We call it as a tree. What is the definition of a tree? A tree is a graph which doesn't have a cycle. So since our spanning graph doesn't have a cycle, so we can also call it as a spanning tree. So the spanning tree and spanning subgraph will be called interchangeably. They will be used interchangeably. They mean one and the same. So minimum spanning tree. A minimum spanning tree is a tree in which sum of all the weights over the edges is minimum. As possible, as much as possible, it should be minimum. In our previous example, we had come across many subgraphs and we have taken only few of them. Among these spanning subgraphs, the one which is minimum is the fourth one, the last one, A to B, B to C, C to D, which will weigh only 7. The sum of all the edges, 4 plus 1 plus 2 is equal to 7. So among all the possible subgraphs, spanning subgraphs, the one with minimum weight was A to B, B to C, C to D. So this is a minimum spanning tree or minimum spanning subgraph from a graph. So there are two different methods of finding out minimum spanning graph or minimum spanning tree. Two methods. They are Prim's algorithm and Kruskal's algorithm. Prim's algorithm. Prim's algorithm is a greedy algorithm that finds minimum spanning tree for a connected, weighted, undirected graph. That is, Prim's algorithm is used to find the minimum spanning tree, wherein the minimum spanning tree has a subset of all the edges and vertices that are there in the original graph. Prim's algorithm is a minimum spanning tree algorithm that takes a graph as an input and finds the subset of the edges of that graph which form a tree that includes every vertex that has the minimum sum of weights among all the trees that can be formed from the graph. So that is minimum spanning tree algorithm. Prim's algorithm takes the graph as an input and finds the subset of all the edges of that graph, from which we form trees which include every vertex that are there in a main graph, and the sum of the edges which will lead to minimum weight will be considered as the minimum spanning tree. Steps to implement Prim's algorithm are: you initialize a minimum spanning tree with a vertex chosen at random. That is, to create or to find out the Prim's minimum spanning tree, we choose one of the vertex randomly, any vertex from the input graph as an initial vertex. Then find all the edges that are connected. Then find all the edges that connect the tree to new vertices. Find the minimum and then add it to the tree. That is, you take one vertex randomly as a root vertex or the initial vertex, then find out the adjacent vertices to this vertex. Among the adjacent vertices, the one which is found with the minimum edge will be chosen and added up to this tree, and this will continue until all the vertices from the main graph are added to the tree, and making sure that no cycles are formed by adding a new edge to the tree. Some of the definitions which are related to this graph. So we call unseen edge an edge with both vertices not in Ti. That is, when we write an algorithm, we have two set of vertices, V and V dash. V dash is a set of vertices in a tree. So an edge with both the vertices in a tree are called as unseen edge. An edge which has one vertex partially constructed in a tree and the other is not. That is, suppose if you have a vertex A and B and an edge is connected between A and B. If we begin our Prim's algorithm, we start to create an minimum spanning graph. So we choose one vertex as a random vertex and take it as an initial vertex. Suppose if we choose A as the initial vertex, now A is in a set V dash, which is the set of vertices in a tree Ti, but B is not yet been visited. So A is called as unseen edge, and fringe, it is an edge that has one vertex partially in vertices of tree and the other one is not. So the edge that is connecting A and B is called as fringe edge, which has one vertex in the tree set and the other vertex is out of the tree. So these two are different definitions that will be used for them. So here we have an algorithm. So how it works, I'll tell you. Let G be a graph with set of vertices V and edges E. As I said, Prim's algorithm will take a graph as an input. So G is a graph with vertices set V and edge set capital E. It is connected, undirected, weighted graph. In the second step, we create two sets of vertices V and V dash, where V dash is an empty set, that is a set of vertices which are present in spanning tree. Initially, we have no spanning tree, we are yet to find out. So, the set of vertices in a tree is empty, that is V dash is empty, and V contains all the vertices. V contains all the vertices that are in a graph G. In the second step, we start selecting the minimum weight edge V, U from a graph G and insert that edge into a edge set E dash and the vertices into V dash. That is, we have to, for a current vertex, find out the next adjacent vertex which is connected to E, and that is how it is connected through the edge. So, we find out an edge which has minimum weight, and that edge we consider as V, U. And now insert the minimum edge into the E dash edge set of tree, spanning tree T, and the vertices that is newly found using the edge is added up again into V dash. And here V dash is a set of vertices which are visited, and V are the set of vertices which are unvisited, that is all the vertices in a V which are unvisited. We can also say that V is equal to V dash minus V. Now repeat the step 2 until all the vertices in V are in V dash. That is, we traverse all the vertices in V and all the vertices are added into a set called as V dash. That is, set of vertices in a spanning tree T. Find the neighbors of all the vertices in set V dash such that one end point is in V dash and the other one is not in V dash. That is, one vertex is visited and the other vertex is unvisited. This means that we have to find the minimum edge in the graph which has one of its endpoint in V and another endpoint in V dash. That is, one is already visited, the other vertex is unvisited. Now after we finish visiting all the vertices and get all the vertices from a graph G into vertex set V dash, we sum up all the edges and then we come up with the weight, that is minimum weight. This is how Prim's algorithm works. Now let us see the algorithm of Prim's. Algorithm Prim's, which has an input G. Prim's algorithm for constructing minimum spanning tree, that is MST, minimum spanning tree. Prim's algorithm for constructing minimum spanning tree MST. And the input for this algorithm is a connected graph G with a set of vertices V and E. Output is the edge set of tree, the set of edges that compose minimum spanning tree of a graph G. The set of trees vertices can be initialized with any vertex. That is, we can begin our tree from any vertex. We can randomly pick any vertex. So initially Vt is V0. That is, we begin our creation of spanning tree with the initial vertex. So we pick randomly any vertex. Here we have taken V0, or you can even initialize it to null. Then we begin traversing one by one. Since a graph with n vertices will have n minus 1 edges, so our for loop will begin from I is equal to 1 to vertex minus 1, that is number of vertices minus 1. So we find out the minimum weighted edge E star, which has two vertices V star and U star among all the edges V comma U. A graph has a different set of edges V comma U, many pairs. We choose one pair V star and U star which is having minimum weight, and that edge is added into E dash, that is edge set E or ET, and the vertices are added into VT. such that V is in Vt, that is the vertex that we have visited, we have already visited, is in V3, V dash, and U, that is newly being visited vertex, is in V, a graph where it has not yet been visited. So V star, U star sees that V star is a vertex in tree and U star is a vertex in a graph which is unvisited. So the edge, new edge will be considered or added up into the tree Vt. So Vt is equal to Vt union U star. That is, in the vertex set Vt, you add up a new vertex U star which is being visited newly. And in a edge set Et, you unite or add up a new edge U star V star into Et, and it is newly added up will be newly visited edge will be entered into Et. So this way you keep on visiting the new vertices until you visit all the vertices in your graph. And one more important thing, in a Prim's algorithm, it is very important that when we start finding out the spanning tree for a given graph, it is very much important that we delete or remove all the loops and multiple edges or parallel edges from a graph. Only then we can implement Prim's algorithm. That is why in a for loop we have taken I is equal to 1 to v minus 1, that is n minus 1. If it is a normally connected graph with no loops and with no parallel edges, a graph with n vertices will have n minus 1 edges. So the Prim's algorithm will begin with the edges. We keep on trying to add up edge set into a tree. So here we have an example of an Prim's algorithm. This is a graph. So let us begin. So this is a graph with vertices A, B, C, D, E, F with the weights over the edges. So let us begin. So this is how we solve our Prim's algorithm to find out the minimum spanning tree. So let us have three partition, tree vertices, the vertices in a graph G, and the remaining vertices in a graph. And then the third part is graph, that is a graph or spanning graph that we are creating. So we begin our Prim's algorithm. As we said in the algorithm, we pick any vertex, randomly pick any vertex as the initial vertex, A, B, C, D, E, F. We have 6 vertices in a graph. We may pick any one of them. So if I go alphabetically and I take A as the initial vertex. So I've taken A as the initial vertex. So here I have A within bracket dash comma dash. So what are these spaces? The first dash will tell you the parent vertex of this vertex. That is when we say U star V, reaching V from U. So A comma B in the sense A to B. So if you reach B from A is called as the parent vertex. So A of dash comma dash. Why it is dash comma dash? So from A, we have my initial vertex is A, so it has no parent vertex, so that is why it is dash. What about the next dash? So next dash is the distance, weight over the edge. Weight over the edge. Since A is the initial vertex that is being visited and we have not yet been traversed any of the edges, so no edge with the weight has been traversed, so that is why it is blank. So A of dash comma dash, because it has no parent vertex and no distance has been covered to reach A. So the next column, that is remaining vertices. So what are the remaining vertices in your graph G? So I have visited A as initial vertex. What are the left out vertices? I have B, C, D, E, F. B, C, D, E, F. So look at the graph. So if I have taken E as initial vertex, A is adjacent to B, F, E. Right? So if I go from A to B, what is the weight? 3 is the weight. And if I reach from A to B, B is the visited node and which has the parent node as A, and the distance to be covered to reach B from A is 3. So it is B of A comma 3. So you can see B of A comma 3 because you reach to B from A is a parent node, B is your next visited node and the distance covered is 3. So that is why B of A comma 3. Next, from A I can even reach to F. So that is why I write F of A comma 5. That is next visited vertex will maybe F, which has a parent node as A and the distance covered will be 5. So F of A comma 5. Similarly, E of A comma 6. I have written E of A comma 6. So 3 adjacent nodes to A, B, E and F, and the distance covered will be to reach B is 3, to reach E it is 6, to reach F it is 5 from the graph. So that is why we write B of A comma 3, F of A comma 5 and E of A comma 6. So how about C and D? Since there is no direct edge from A to C and A to D, you cannot reach. So it is distance is taken as infinity. So we write D of dash because we have not yet reached to C and we do not have any parent node, so it is dash and the distance is infinity, which is initially taken as infinity. D is also dash comma infinity. So the next part, graph. So here initially I have to take only A and from, so it is only A. Next when I come among A, B, C, D, F, sorry, B, C, D, E, F, the one which is minimum, which is the minimum one from A I can reach to B, look at the graph, from A I can reach to B with distance 3, from A I can reach to F with distance 5, from A I can reach to E with the distance 6. Among these three, which is the one which is having minimum distance? It is 3, that is from A to B. So the next vertex that I visit will be B with the distance 3. So U is A and B is V. So the next vertex I visit is B. So I add up in my graph A to B with the distance 3. So when I have the vertices in a tree, now I have visited 2 vertices in my tree. So my tree has 2 vertices A and B. So B of A comma 3. And what are the unvisited remaining vertices in my graph? C, D, E, F. C, D, E, F. So look at the graph. So I have reached from A to B. So left out is C, D, E, F. From B, I can reach to C with the distance 1. From B, I can reach to F with distance 4. And from A, I can reach to E with 6. And so there are only these 2 visited vertices. Now find out all the other vertices that can be visited with the help of A and B. So with the help of A and B, I can only visit 3 vertices, that is C, F, E. So I write it here. C, from B I can reach and the distance is 1. From A I can reach to E with the distance 6 and from B I can reach to F with the distance 4. You can notice here F could be reached from A with a distance 5. F can also be reached by B with a distance 4. So when I choose the minimum. So if I choose the next vertex as F, it would be better for me to reach from B rather than A, where A cost me 5, B is costing me 4. So I have changed here F of B comma 4 instead of F of A comma 5. So if I reach to F from B, my parent node will be B and the distance will be 4. So that is why in the second row I have taken C of B comma 1, D of dash comma infinity, E of A comma 6, F of B comma 4. So among these 4 nodes, which is the one which is having minimum distance, definitely it is C, C of B comma 1. So the next vertex that I visit will be C with the distance 1. So add it up in your spanning graph. A, B, C. A to B is 3, B to C is 1. So move on next. So I have 3 vertices in my tree, A, B, C. C is a vertex that is reached from. So what are the remaining vertices I have in my graph? Go back to graph. So I have reached A, B, C. Remaining vertices are F, D, E. So for F, I can reach from C or B, both will cost me 4. So since I have already taken B to F as 4, no need to change C to 4, because you change the parent node only when the becomes less. That is, if C to F was 3, I would have changed F of C comma 3. But F of C comma 4 or F of B comma 4 are one and the same. So need not change. So it will be F of B comma 4 same. So that is why I have taken F of B comma 4. So the next unvisited vertex is E. So E can be reached from A, that is 6. So I have taken E can be reached from A, that is 6. And D. The next vertex D can be reached. Now newly found D vertex is C. D is reachable now from the vertex parent node as C. So D of C comma 6. So I have taken D of C comma 6. So the remaining vertices are D, E, F, D of C comma 6, E of A comma 6, F of B comma 4. Among these three nodes, which is the next vertex that I can visit with minimum vertex, with minimum edge, weight on the edge, 4. So that is why the next vertex I reach is F. So here I have a graph A to B, B to C and B to F. Moving on further. So from F I can reach to E. So I have taken A, B, C and F. So two more edges are vertices are remaining D and E. Now find out the edges that will take me to E and D with minimum cost. So I can reach to E from F with a distance to, I can reach to D with from C, which is having the distance 6. So here you can notice 2D I can even reach from F also. So from F it will cost me 5. So I'll change now reaching to D from F with the cost 5. So I've changed it from to F from D with the cost of 5. So among E and D, the next visited vertex will be E because it has the minimum edge cost, that is 2. So here I have my graph A to B, B to C, B to F and F to E. So the next remaining vertex is D. So I can reach to, go back to graph, I can reach to E with all the four, I can reach to E from A, from F, from D. From A it will cost me 6, from F it will cost me 2, from D it will cost me 8, which is the one which is minimum, that is from F, which is costing me only. So the next vertex, I'm sorry, I have to have the next left out vertex is D. So D, to reach D I can go from F, I can go from C, I can go for E. To reach to D from C it is costing me 6, from F it is 5, from E it is 8. So we have already changed D of F comma 5, there is no difference. So the next vertex that will be visited is D. So should I add it? I can add it because it is not forming me a cycle. So the next last visited vertex is D and from F and it has been added. So each time you try to add a edge into your tree, once check whether it is forming a cycle. If it is forming a cycle, discard the choice, go for the next one. So this is how our Prim's algorithm works. So in the next video, we'll be discussing about Kruskal's algorithm.